All right, and some students asked me to explain question 11 of tutorial 11. So here is my explanation. So here we have a differential equation that uses dx and dy rather than dy over dx. So, and we're supposed to find an integrating factor in the form x to the r times y to the s, and then proceed to solve the differential equation, right? So how do we do that? So to do that, well, you should understand what an integrating factor is. So an integrating factor is something that you multiply this differential equation with, and then it becomes exact after multiplication, right? So we've got to write to multiply the whole thing by x to the r times y to the s. All right, so doing that, I will get the following thing. So I will get, so x to the r times y to the s divided by y is going to be, what is going to be x to the r times y to the s minus 1 minus x to the r minus 1 times y to the s dx plus, now I've got to multiply x to the r times y to the s by this thing. So doing that, I will get x to the r plus 1 times y to the s minus 2 minus 2 x to the r y. So now I'm multiplying with this s minus 1 dy, right? Okay, and this is 0. And basically, what we expect is that this new differential equation is exact, right? So what does it mean? So it means that if whatever coefficient we have at dx, if we denote it by m, and the coefficient at dy is n, then basically what you should have in mind is that m should be some potential function differentiated with respect to x, and n should be some potential function differentiated with respect to y, right? But then if you differentiate m with respect to y, then you're going to get the second partial derivative of u with respect to x, y, and the same as if you differentiate n with respect to x, right? So the condition of exactness is that the partial derivative of m with respect to y should be the same as the partial derivative of n with respect to x. Okay, so that's basically the condition. All right, so here is our differential equation again. So let me again rewrite it in the multiplied by the integrating factor. So it's rx to the r y to the s minus 1 minus x to the r minus 1 y to the s dx plus x to the r plus 1 y to the s minus 2 minus 2 x to the r y to the s minus 1 dy is 0, right? So now I've multiplied with the integrating factor. So now I've got to differentiate this with respect to y. And this is what? This is s minus 1 times x to the r times y to the s minus 2 minus s x to the r minus 1 y to the s minus 1. Okay, and now I've got to differentiate this with respect to x, right? So this is like m and this is n. Okay, so differentiating the coefficient at y with respect to x, I will get x to the, sorry, r plus 1 times x to the r times y to the s minus 2 minus 2r x to the r minus 1 times y to the s minus 1. All right, and the condition that must be fulfilled is that this equals this. All right, so but then basically notice that we have the same term here. So for them to be equal, the coefficient in front of them should be equal. Same thing here, right? So for these two terms to be, so these two terms are equal. So for the whole thing to be equal, the coefficients in front of them should be equal. right? So in order for my to be equal to nx, we must have the same following condition should be satisfied. So s minus 1 should be the same as r plus 1, and s should be the same as 2r, right? Okay, so this is a system of simultaneous equations. From the second equation, s equals 2r, so we can just substitute 2r as s into the first equation. So 2r minus 1 equals r plus 1. I guess we can move r to the left, minus 1 to the right. So r is going to be 2, and s equals 2r, which is 2 times 2, which is 4. All right, so basically that's the answer to the first part. So the integrating factor is x2 squared times y to the 4. So that's the integrating factor. So now we've got to solve the differential equation, right? So let me now rewrite the differential equation multiplied by the integrating factor. So multiplying with the integrating factor, we're going to get x squared y cubed minus x y to the 4 dx plus x cubed y squared minus 2x squared y cubed dy. And this differential equation is guaranteed to be exact, right? So which means that there is some potential function, and the coefficient in front of x is the derivative of this potential function with respect to x, and the coefficient in front of dy is the derivative of this potential function with respect to y. Okay, and the question is to find this potential function. So basically, well, we are given the derivative of this potential function with respect to x, right? So the potential function itself is going to be the antiderivative, right? So it's going to be x squared y cubed minus x y to the 4 dx. So integrating this, we're going to get x cubed y cubed over 3 minus x squared y to the 4 over 2. Generally speaking, probably plus some constant. Well, not constant, but rather some function of y. So now the partial derivative of u with respect to y, so we can differentiate this with respect to y. So this is going to be what x cubed y squared minus 2x squared y cubed plus c prime of y, and this is supposed to be equal to to this, sorry, to this thing, which actually it is, right? So we don't even need c prime of y. So essentially c prime of y is 0. So it means that there's no need in any function of y here, so we can just forget about it, so we don't really need it, so we can just forget about it, and this is going to be our answer. So there you go. Okay, so this is the potential function, which means that the general solution to our differential equation is given by the condition that the potential is constant. So x cubed y cubed over 3 minus x squared y to the 4 over 2 is constant. And if we could solve for y or for x, then we probably should do it, but here we can't really. So that's the final answer.